Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to discuss isomers for carbohydrates. And so that includes monosaccharides, disaccharides, and polysaccharides. And so the type of isomerism that we're going to focus on for carbohydrates is known as optical isomerism. So what I would like to do first is just to kind of review the different types of isomers that we've discussed, and then we'll go ahead and talk about optical isomerism. Hopefully you guys, after discussing all these different types of isomers or isomerisms, you guys understand the differences among them. And so, just the word isomers in general informs us as readers, the audience, etc., that we have a group of molecules that have the same chemical formula, but something about those groups of molecules are different, whether they're structurally different, meaning the connections between like the carbons and hydrogens and the oxygens and the sulfurs, or the connections just in general between two or more atoms are distinctly different with respect to each other, or they're spatially different. And so we'll talk about the idea or the differences between structural and spatial arrangement by looking at these examples down at the bottom of the screen. And so let's see here. If we compare trans 2-butene and 1-butene, I want you guys to notice that these two molecules have the same number of carbons and have the same number of hydrogens. We can even count. So here we have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. And so the number of hydrogens that 1-butene has 2, 3, 5, plus 3 is 8. For trans 2-butene, here we have 3, 4, 5, plus 3 is 8. So it looks like trans 2-butene and 1-butene have the same chemical formula, yet they don't look anything similar to each other. And so this is the scenario in which you guys have constitutional isomers. And so constitutional isomers focuses on differences in structural arrangement. So I want you guys to notice that the double bond in trans 2-butene is on carbon number 2 and carbon number 3, whereas the double bond in 1-butene is on carbon number 1 and carbon number 2. And so just that, one example demonstrates that there is a structural difference between trans 2-butene and 1-butene. I can even highlight carbon number 3. And so if you guys look at carbon number 3, notice that there are 2 hydrogens on 1-butene. However, there's only 1 hydrogen in trans 2-butene. And so that alone, those 2 simple pieces of evidence, is sufficient enough to conclude that both of these molecules are constitutional or structural isomers of each other. Now, when you guys are looking at these 2 molecules, cis 2-butene and trans 2-butene, I'm going to erase some stuff here. So I want you guys to notice that there are strong similarities between them, such that carbon number 2 and carbon number 3, they both have, that double bond. So what makes them different is the positioning of the hydrogens and the alkyl groups. And so if I simply focus on carbon 3, notice that CH3 is more or less on the top right-hand corner for cis 2-butene. However, for trans 2-butene, it's found on the bottom right-hand corner. And so one might say, well, why don't you just rotate the double bond so that they're both the same? So if you guys recall, for double bonds, they are kind of locked in a fixed position. You guys cannot rotate the double bond, unlike single bonds, right? So if you guys can imagine, having two pencils between your fists, and you are trying to rotate your fist, at some point in time, the fact that you have two pencils will not allow you to rotate those fists very readily, compared to just having one pencil that's between both of your guys' fists. And so because there is a locked conformation due to the presence of the double bond, these two methyl groups and these two hydrogens will never be able to overlap with these two hydrogens and these two methyl groups. And so what we're looking at is differences in spatial arrangement. And if this differences in spatial arrangement is caused by double bonds, then this would be known as geometric isomers. And so what we're going to explore today is differences in spatial arrangement. So we're still talking about stereoisomers. However, we're going to look at spatial arrangements, differences in spatial arrangements that do not have a double bond in the parent chain of that organic compound. And so we can go ahead and create like this flow chart, if you will, just to kind of help us organize our train of thought. So stereoisomers describe differences in spatial arrangement. And so if the difference in spatial arrangement is caused by double bonds, or presence of double bonds on the carbon chain, then you could potentially have geometric isomerism, in which there is a cis conformation, there's a trans conformation. However, if there is no double bond, so here we're talking about a single bond, differences in spatial arrangement can also occur. And so that type of spatial arrangement is known as optical isomerism or optical isomers. And so when you have optical isomers, instead of saying cis and trans, we're going to say plus enantiomer or minus enantiomer. And so the plus and the minus was derived by how these specific isomers or specific enantiomers bend polarized light. And so the reason why, so this plus and this minus indicates how these enantiomers, or how these groups of organic compounds bend polarized light. So this is the reason why this is known as optical isomers. And we'll discuss more about like the technique later down this lecture video. And so instead of saying, once again, cis and trans, which is very specific to geometric isomers, optical isomers, we're going to use enantiomers to describe the relationship between two optical isomers. Okay. And so one way to think about the use of enantiomers is, so for example, like family. And so you have, if you want to describe the relationship between a brother and sister, you would say that they're siblings. And so the word brother and sister would probably be relevant to, would be analogous to, the use of plus and minus. And the word enantiomer is synonymous or analogous to using the word siblings to describe the relationship between two individuals that belong to the same family. And so what I want to explore is what makes these molecules optical isomers. And so I want to do this by taking a look at L-lactic acid and D-lactic acid. And so if I were to draw a line between these two molecules, I want you guys to go ahead and kind of zoom out. I'll zoom out just a little bit. Take a step back, and I want you to think about how these two molecules are related to each other. Like, what word would you describe the relationship between these two molecules? Okay. And so if you had said that they're, like reflections of each other, then you guys are on the right track. And so enantiomers describe two compounds that are mirror images of each other. However, these compounds are non-superimposable. And so if you have a mirror image of a compound, or if both of those compounds are mirror images of each other, and then you put them right on top of each other, and not all of those atoms line up, then, in other words, are non-superimposable, then the relationship between these two molecules are known as enantiomers. Okay? And therefore, broadly speaking, they're known as optical isomers. Now, whether or not they're plus or minus, that's going to be a topic that I want to discuss a little bit later on. But I just want you guys to understand how these terminologies connect. And so once again, if you have two or more molecules that are mirror images of each other, and if you were to take both of those molecules and superimpose them on top of each other, if even one atom does not line up very well, or it does not line up perfectly, then you would say that those two molecules are enantiomers of each other. Okay. All right, so what I want to do is I want us to understand, or just kind of discern what feature within this compound that makes this whole entire molecule, both these molecules, non-superimposable. Okay. And so I went ahead and kind of drew this structure here that's present on your screen. And so I want to go ahead and talk about these bonds first. So we know what these lines mean, right? Those are single bonds, double bonds. And if they're just like normal lines, like how you guys normally depict covalent bonds, then you're communicating to the reader that all of these atoms that's bonded to this central carbon are in plane to this carbon, right? And so if you guys are using this kind of wedged notation to describe the double bond, then that means that this atom is protruding upwards, if you will, with respect to the central carbon. And if you guys are using this dashed line, I know I've used this dashed line before to represent like an intermolecular force. However, this dashed line that's present inside a covalently bonded molecule basically represents a bond such that this hydrogen falls underneath or below that central carbon. And so to kind of better demonstrate this, I'm going to go ahead and just kind of scoot this molecule right next to the L-lactic acid. And so looking at this ball and stick model, we can kind of see the three-dimensional aspect of L-lactic acid. And so I want us to focus on this central carbon, which represents this central carbon. Notice that this bond here that I'm highlighting or I'm outlining in blue, it's sticking up with respect to this black sphere, which is going to represent the carbon. And so I want you guys to imagine that L-lactic acid is a person that you're facing. And this carbon that's in the middle is going to represent the torso of the person that you guys are facing. And so in this image that I'm trying to describe, these bonds are going to represent the arms, and these spheres is going to represent like the fist. And so if the person that you guys are facing is in a position such that they look like they're zombies, and so in other words, both of their arms are kind of like raised up, their fists is in front of this, their fist is in front of the torso, and the torso represents this black carbon. And so basically these blue lines that I'm highlighting here is representing this wedged bond. And that is telling the reader that this hydrogen in this hydroxyl group is above the plane of carbon. In other words, it's sticking up at you. Now, if you guys are looking at these dashed lines represent bonds that are going behind the plane of the carbon. And so in this idea of this person that you're looking at, the arms would be going behind the torso, right? So it's as if you guys are swinging your arms back. So the person that you're looking at is swinging their arms back, and therefore the arms, which represents the bond, is behind the plane of the torso. And so that's what these dashed lines represent. Okay. All right, so hopefully you guys kind of understand my description. This would be a different story if we were, if I was teaching this in class, so I wouldn't be doing this digitally. So anyways, hopefully you guys understood that analogy. Keep that in mind when we're talking about this idea of things that are superimposable, things that are non-superimposable. All right. And so once again, just to get back to the main topic, enantiomers describe these molecules that are mirror images of each other, and they are non-superimposable. And so what we want to do is we want to determine what part of that molecule contributes to the fact that these molecules are not superimposable. Okay? So that's the premise that we're working on. And so what I'm going to do is I'm going to take this molecule and I am going to superimpose it on this molecule. Okay? So I want you guys to look, I'm just going to go up and down, right? And so I want you guys to look at the positions of the atoms and the bonds. Okay. And so if I allow it, if I just don't move this stuff anymore, which carbon in this view, in this perspective, allows the molecule to look like they're superimposed? Okay. And so if I were to separate them out, notice that the carbon at the bottom, the last carbon, the hydrogens that surrounds that carbon, the use of the bonds, the dashed lines and the wedged, fall exactly on top of each other. And so we can conclude that the last carbon allows that part of the molecule to be superimposable. Okay. And so if I were to once again drag this molecule and try to superimpose it, notice that the molecule on the top doesn't look like they're readily superimposable, right? So we have an OH on the left-hand side and a carbon that's double bonded on the oxygen also on the left-hand side. Now, if you guys recall, single bonds, they're able to rotate freely. And so what that means is that I can rotate this about 180 degrees such that this double bond to the oxygen is simply going to be on the opposite side once it's rotated 180 degrees. Okay. And so if I were to now pick up this molecule and drag it, notice that the carbonyl group and that hydroxyl group are now superimposable. Okay, so here we have the OH is lining up, the carbonyl is lining up. And so if I were to rotate it 180 degrees, it looks like the first carbon is also superimposable. And so therefore does not contribute to this idea that the molecule is an enantiomer. And so the last thing that I want to discuss is this carbon that's right in the middle. So from here on out, we're going to be focused on the carbon that's right in the middle. Now, if I were to take this molecule and drag it and place it on top of each other, notice that the hydrogen that's on the left, that's moving, does not match the OH that's on the left. And I'm talking about the middle carbon here. Where the middle carbon that's moving, the OH does not match to that hydrogen on the right-hand side. And so even though the wedged bonds kind of overlap, the identity of the atoms themselves do not match on the left or right-hand side. Well, one can go ahead and argue that if you rotate this 180 degrees, right, because remember these are single bonds, and as long as we have single bonds, we can rotate these bonds freely however we like. And so if you rotate those two single bonds by 180 degrees, it would force the OH that's on the right-hand side to be on the left-hand side, and it would force this hydrogen that's on the left-hand side to go on the right-hand side. And so one might say, okay, well, if the OH and H is kind of flipped places, then it looks like the carbon in the middle will be able to be superimposed to the molecule that's on the left. Now, the answer to that, well, it's not, I actually never posed a question, but the one thing that you guys have to keep in mind is that the carbon itself, the central carbon, is tetrahedral. So what that means is that if you actually rotate it 180 degrees and flipping the position of the OH and the H, those hydroxyl groups will no longer have the bold line or the wedged line. It's actually going to have a dashed line. In other words, I want you guys, now this is where the analogy of the zombie kind of kicks in. And so imagine that you guys are staring at a zombie, and typically like these zombies, they have their arms in front of their torso, right? And so if you freeze that zombie and if you rotate it 180 degrees, so basically you're just flipping it, where would those arms lie with respect to the torso of the body? And so instead of those arms going, instead of those arms facing you, pointing at you, they would now go behind, right? They would be pointing away from you. And so if you rotate this 180 degrees, I'm going to go ahead and kind of copy and paste, or not copy and paste, duplicate. What would happen is that, yeah, the OH and H would flip, but the bond will also flip. So instead of it being bold or wedged, it would now be dashed, meaning that the OH and the hydrogen are behind the plane of the carbon. And so if you overlap this molecule with its mirror image, let me go back. And so if you overlap this molecule, notice that the identity of the elements now match. So you can see on the left-hand side with respect to the middle carbon that the OHs match, and on the right-hand side of the central carbon, the hydrogens now match, but the bonds don't match. Notice that the bond, one bond is dashed and the other bond is bold or wedged. And so because the bonds don't match, then it is the central carbon that makes the entire molecule non-superimposable. And so we would say that this carbon is chiral. So you can think of chiral carbons as this carbon that makes this whole entire molecule non-superimposable. Okay? And so if you have even just one carbon that's chiral, then the whole entire molecule is chiral. Therefore, if those molecules are mirror images of each other, there is no possible way in which those molecules, there's no possible way that every single one of those atoms in that molecule will be superimposable if you have a chiral carbon that is present. Okay. And so once again, just rotating the bonds 180 degrees, yeah, it would flip the OHs and the H in the middle of the carbon, but it also flips the type of bond that's drawn. And so instead of it being, bold or wedged, it would be dashed. And so therefore, it would, there's no way that those molecules can overlap. And so I want you guys just to imagine, I know this is kind of tough to communicate digitally, But I want you guys to imagine that if you guys rotate this 180 degrees, this hydrogen would be pointing backwards. Okay, so the hydrogen is now here, and then this OH is going to be pointing behind. Okay? And so if you guys are trying to overlap these two carbons, this hydrogen and this OH is pointing up, whereas when you rotate them 180 degrees, that OH and this hydrogen is pointing down. And so because their bonds do not overlap, that carbon is going to be considered non-superimposable. So it's going to be a chiral carbon. All right. And so let's go ahead and talk about this idea of chirality. And so chiral molecules produce a mirror image that is non-superimposable. So if you lay them on top of each other, there's going to be some pieces will fit, but there is always that one piece of the molecule that will never align perfectly. And so that occurs if you have a chiral carbon. So an achiral molecule means that the mirror images are superimposable. And so if your mirror image is superimposable, then that means you have the same exact molecule, and therefore they are not enantiomers. If you guys have a chiral center, chiral carbon, that makes the whole molecule chiral, so you have a chiral molecule, and therefore its mirror image is non-superimposable. So therefore, those molecules are distinct from each other. And so, therefore, we would say that those molecules are enantiomers of each other. And so an example of a chiral object is your left and right hand. So if you just simply superimpose them, or put your hands on top of each other, your thumbs will not overlap. And so if you guys look at a flask, and if you were to draw its mirror image and then superimpose its mirror image, notice that both flasks overlap. And so because those flasks overlap, because they are superimposable, then you would say that that object is achiral. In other words, both of these objects are the same exact thing. However, both these objects, because they are chiral, they are not the same. And we would say that our right hand is an enantiomer of our left hand. Okay? And so their spatial arrangement, how they're arranged in three-dimensional space, is different, making them different molecules. Okay. And so we're going to go through a couple of exercises that will hopefully demonstrate the idea of chirality. And then we're going to look at how we can kind of streamline the process to identify if our molecule is chiral. And this is done by determining if there's a chiral carbon in our organic compound. So let's go ahead and take a look at this structure. So we have bromochlorofluoromethane. And so in this image, we have this molecule that's on the left, and its mirror image is already drawn on the right side, on the right-hand side of this mirror, so to speak. And so what we want to do is we want to check if these molecules are chiral or achiral. And one way to do that is to rotate one of these two images 180 degrees. And so we have to keep in mind that carbons are tetrahedral. There's a three-dimensional geometry. It's not flat. So when you guys are doing 180 rotations, 180-degree rotations, you have to represent that using a bold or a wedged line or a dashed line. And so remember, this bold or dashed line is representing that this chlorine is pointing more towards you. So it's above the plane of this carbon center. And so a dashed line is going to represent a covalent bond that is behind the plane of this central carbon. So it's as if somebody's arm, if you guys are looking at them, is behind their torso. Okay. And so when you guys are performing 180-degree rotations for these molecules, it's pretty simple, right? And so let's go ahead and set up some rules. So if you have a wedged or bold line, when you take when you rotate it 180 degrees, a bold will become dashed. And conversely, if you have something that's dashed, and if you rotate it 180 degrees, you get a bold line. And so if you have a normal line, and if you rotate it 180 degrees, you'll still get a normal line. Okay. So for those who are able to rotate this in their mind, they have. If you guys have, strong spatial organization, or what do they call it, spatial intellect or something like that, then this shouldn't be an issue for you to do. However, if it's difficult for you to imagine this rotation in your head, you guys can go ahead and use these rules to help you draw this out. And so a bold becomes dashed, a dash becomes bold, and the normal stays as normal. And so what we're going to do is we're going to take a 180-degree rotation for this molecule, for this mirror image. And so I'll just go ahead and do it right underneath so that you guys can see what I'm doing. And so notice that if I take 180 degrees if I rotate this guy 180 degrees, and I actually do have to set up a premise here. So the 180-degree rotation is going to happen around the vertical. Okay. And so if you rotate that hydrogen that's at the very top 180 degrees, is it going to go anywhere? And the answer is no. So it's just going to stay at the top. Now, if you were to rotate this fluorine with a normal line 180 degrees, it would now be found on the opposite side, but the depiction of that bond is still going to be a normal line. Okay. Now, if I rotate this 180 degrees, then this chlorine is going to flip, but then it's going to become a dashed line. Okay, so we go from bold to dashed when we do 180-degree rotation around the vertical. And so here we have this BR. When you rotate that 180 degrees, it's going to be found in the opposite side, and the bond goes from dash to bold. Okay. And so this is the result that we get after we take this molecule and rotate it 180 degrees around the vertical. And so to check if this molecule is an enantiomer, we're going to take our rotated product and we're going to overlap it with the original structure. So I want you guys to notice that the hydrogens overlap and the fluorines overlap. However, if you look at the chlorines and the bromines, they do not overlap at all. So if you guys look at the chlorine is dashed it's the structure that I'm moving, whereas the chlorine that's stagnant is bold, right? And so already there's no way that those chlorines will overlap. Same thing with the bromines. One bromine is bold and the other bromine is dashed. And so because these two molecules are non-superimposable, then you would say that both of these molecules are enantiomers of each other and therefore are completely different molecules, right? And so these are enantiomers. Now, whether or not they're plus enantiomers or minus enantiomers, you guys would need more information. But for now, we can go ahead and say that they're siblings of each other. They're not exactly the same molecule, but they're related. Okay, and their relation is the fact that they have the same chemical formula. But honestly, these are two different molecules completely. And so hopefully that exercise helps you understand how to rotate things 180 degrees. So once again, to check if your molecule, your simple molecule, is chiral, or if these mirror images are enantiomers of each other, you just want to take one of those molecules, rotate it 180 degrees around the vertical, and then overlap it with the other compound that you didn't rotate, and see if every single atom and bond aligns. If not, then you guys have two completely different molecules, and their relationship to each other is that they're enantiomers of each other. Okay? And the carbon that holds them together are chiral. And so in other words, these chiral carbons produces a mirror image molecule that's not superimposable. All right, and so let's go ahead and apply that same idea again to dichlorofluoromethane. And so what we're going to do is we are going to check if these mirror images are superimposable. And so if these images are superimposable, then that means that they're the exact same molecule, and they should not be labeled as enantiomers. And so what we're going to do is we're going to rotate this molecule around the vertical 180 degrees. And I'm going to go ahead and just kind of draw the result at the very bottom here. And so if you guys are looking at this hydrogen, if you rotate that hydrogen at the top 180 degrees around the vertical, it's not really going to change its position. It's still going to stay on top. And so here we have that central carbon. And so this fluorine, if you rotate it 180 degrees, it would be found on the opposite side. And the type of bond that it would have, it would still be a normal line. Okay. All right. And so let's go ahead and take a look at this chlorine. So notice that this chlorine has a bold covalent bond or wedged line. And so when you take a 180 degree rotation, you're going to go ahead and place that chlorine on the opposite side, and then you're going to change its bond from bold to dashed or wedge to dash. Okay. And so when we take this chlorine and rotate it 180 degrees around the vertical, this chlorine is now going to be found on the opposite side. And we're going to change this dashed line into a bold line or wedged line. And so this is the rotated product that we would get. And so to check if our molecule is superimposable or non-superimposable, we're merely going to drag it on top of each other. And I want you guys to notice that the hydrogens line up, the fluorines line up, they both have the same type of bond. Notice that the chlorines, they line up, in terms of location and in the type of bond. And so since we have a perfect alignment of all of these molecules, we would say that this molecule is achiral, and that their mirror images produce the same exact molecule. They're not not different. So they're basically the same molecule. And so basically, since this molecule is achiral, then this carbon is achiral. It's an achiral center, meaning that the rotation of that carbon in any which way will produce a superimposable, will produce something that's superimposable. Okay. And so since this is an enantiomer, we're going to say that this guy is chiral. This molecule is chiral. All right. And so once again, we're going to go ahead and look at two more examples. And so if you have something that looks like this, and if you want to determine if these two mirror images are chiral or achiral, you want to determine if these molecules are the same or if they're enantiomers. What you want to do is rotate one of your mirrored compounds 180 degrees around the vertical. And so the result, so I'm just going to go ahead and draw my vertical line. And so here in this case, if you guys are looking at the CH3, if you rotate the CH3, it's still going to be CH3. Okay. And so rotating 180 degrees, the position of that CH3 and the type of bond is still going to be the same. And so this OH, when you rotate it around the vertical, it's now going to go to the opposite side, and it's going to be dash instead of bold. Oops. And if I were to take this chlorine and rotate it 180 degrees, then it's going to go to the opposite side, but since it's a normal line, it's still going to be a normal line on the opposite side. Okay. Finally, this hydrogen, since it's on the left-hand side of that line, when you rotate it 180 degrees, it'll be found on the right-hand side, and the bond is going to go from dash to bold, or dash to wedge. And so this is the result of my rotated substance. Now what I'm going to do is I'm going to drag this over to the compound that I didn't rotate, and I'm going to go ahead and overlap it. And I want you guys to notice that the CH3 overlaps perfectly. They have the same bond, same position. The chlorine, same thing, same bond, same position. But if you guys look at the OH and the H, they're not overlapping. One of them has a different bond type, and basically, they just don't overlap at all. And so you would say that these two molecules are completely different to each other. And, they're, in other words, are not the same molecule. They are enantiomers. Okay, so they are two different compounds, and they're only related through this idea of isomerism, meaning that they have the same chemical formula, but they have a different spatial arrangement, making them completely different molecules. And so that lets me know that the carbon is chiral, making this whole molecule chiral with respect to its mirrored image. Okay, so this molecule is also chiral, making this carbon also chiral. All right, so one last example. So once again, we're going to go ahead and check out these two molecules, and we're going to try to determine if these molecules are chiral or achiral. We're going to determine if these molecules are exactly the same or if they are different from each other. And what we're going to do, once again, we're going to draw this vertical line, or, and we're going to rotate this molecule 180 degrees, and we're going to draw the result of it. And so, once again, if we're looking at the top part, if we rotate that 180 degrees, it's not really going to change. It's still going to be in the same position, same type of bond. Since it's a single line or normal line, it's going to be a normal line when we rotate. This chlorine, since it's found on the right-hand side of that vertical line, 180 degree rotation is going to be found on the left. And since it's a normal line in the beginning, it's going to be a normal line at the very end of the rotation. For this hydrogen, it's going to be found on the opposite side, so it's going to be on the right-hand side now. And since it was originally bold, we're going to make a dashed line for that hydrogen. Finally, we're going to go ahead and take a look at this hydrogen on the left-hand side when we rotate it 180 degrees. This hydrogen is now going to be found on the right-hand side, and we're going to transform that dashed line into a bold line or a wedged line. Okay. And so this is going to be the result of our rotated compound. And once again, we're going to go ahead and take this molecule and we're going to superimpose it on the molecule that we didn't really rotate at all. So notice that the CH3s, they match, the lines are the same, the Cls, they match, the lines are the same, the hydrogens, they match, and the type of lines or covalent bonds are the same. Okay, so they're overall the same molecule. And so it looks like the mirror image of the molecule in pink produces the exact same molecule. And so therefore, both of these molecules, I'm going to erase them. I'm going to erase some of this stuff. Both these molecules are the same. And so therefore they are achiral. Their mirror images are superimposable. And since we have achiral molecules, that means that their carbon is also achiral. Okay. And so we have no enantiomers. All right. Cool. So hopefully after going through those 4 examples, you guys kind of get a feel. Hopefully you guys kind of get a feel of this idea of chiral, achiral, enantiomers, and all of that stuff. So remember, enantiomers are a type of isomers that describe 2 molecules that are completely different, and they're completely different because of their spatial arrangement. Even though the number of, even though their chemical formula is the same. All right, so what we're going to do is we're going to apply this into more complex molecules. And so what I'm going to do is I'm going to erase what we've kind of done here. Okay. So there's a point that I want to make. And so based on our work, we've determined that the molecule at the top is an enantiomer. It's chiral. And the molecules at the bottom are not enantiomers. They are achiral. And so what we want to understand is what is the quickest way to identify if something is chiral or something is achiral. And so I want to go ahead and use these two examples to demonstrate a point, to demonstrate that specific point. And so let's go ahead and look at this chiral substance. Notice that here there are 1, 2, 3, 4 different types of attachment to this carbon. And so if I were to scroll up, notice I have 1, 2, 3, 4 different types of attachments to this central carbon. And if I scroll up some more, remember that I mentioned that this carbon was chiral. I have 1, 2, 3, 4 different attachments to this central carbon. And so it looks like the pattern to identify chirality in a molecule, in a complex molecule, is simply to count the number of substituents. Not count the number of substituents, but look at the number of substituents and see if those substituents are the same or different. So long story short, if you guys have 4 substituents, if you will, that's attached to a specific carbon, then that carbon is going to be chiral. And so if you look at molecules that are achiral, you have present on that central carbon at least 2 substituents, or 2 groups of atoms or whatever you wanted to call it, that are exactly the same. And so if you have, if you observe in your organic compound that you have 2 molecules, or sorry, yeah, 2 molecules, or not 2 molecules, 2 atoms or groups of atoms that are attached to the same central carbon, then that central carbon is going to be achiral. Okay? And if you guys have a whole bunch of carbons that are achiral, then overall your molecule is achiral. If you even have just one chiral center, chiral carbon, then that whole molecule becomes chiral. And so we can go ahead and identify molecules that are chiral or achiral simply by looking at what's attached to each of those carbons and see if they are the same or if they're different. Okay. And so what we're going to do is we're going to practice that for expanded structures, and we're going to look at that same concept for the skeletal structure. So let's go ahead and look at this molecule. So this is ethanol. And so I want to determine if ethanol has an enantiomer or if it's simply achiral. So I want to determine if ethanol has another version of itself in which its mirror image is not superimposable to it, making a completely different molecule. And so looking at this carbon that's on the left, I'm just going to count the number of substituents that are the same. And if the number of substituents on that carbon are the same, then that carbon is achiral. So looking at this carbon, here I see 1, 2 hydrogens. So I have the same atom that's bonded to this carbon. And if I have at least 2 that are exactly the same, then that means that this carbon is achiral. Okay. So I'm going to go ahead and look at this carbon on the right. So notice that on this carbon, I have 1, 2 hydrogens. And since these hydrogens are the exact same atom that's bonded to the same exact carbon, then therefore this molecule, or I'm sorry, that carbon is also achiral. And so if all of our carbons are achiral, then overall this molecule is achiral. Meaning that if you were to draw its mirror image, you can take its mirror image and superimpose it onto the original structure, and everything would line up. All right, so let's go ahead and take a look at glycerol. And so glycerol has 3 carbons, so I'm going to check every single carbon to see if they are chiral or achiral. So looking at this carbon on the left, notice that there are 2 hydrogens that's bonded to it. Those hydrogens are the same, so therefore this carbon is achiral. So I want to, let's go ahead and look at the carbon that's in the middle. Notice I have a hydrogen here, an OH here. Okay. And so this carbon is bonded to all of this. Okay. Oops. And this carbon is bonded to all of this. And so notice that both of these are the same. So if both of those are the same, then therefore this carbon is also achiral. Now if you guys are looking at this carbon on the right hand side, so let me erase all this stuff because my perspective and focus is a little bit different now. So if I'm focusing on this carbon, notice that that carbon is bonded to 2 hydrogens, and so therefore that carbon is achiral. And so if all of your carbons are achiral, then that means this whole entire molecule is achiral. Its mirror image will be superimposable to its original. Okay. So we have an achiral molecule. All right, so let's go ahead and take a look at this structure. So this is the somewhat of a condensed structure. So looking at this carbon that's on the left, notice that it's bonded to 3 hydrogens. And so since it's bonded to at least 2 atoms that are the same, that carbon is going to be achiral. So let's go ahead and take a look at this carbon that's on the right. This carbon is bonded to this hydrogen, that's 1. It's bonded to this CH3, that's 2. It's bonded to this SH, that's 3. And it's also bonded to this whole thing. So I want you guys to notice that you have 4 different attachments to this carbon, making the carbon that I'm highlighting in yellow chiral. And so if you have at least 1 chiral carbon, then this whole molecule is chiral. Meaning that if you were to draw its mirror image, that chiral center, that chiral carbon, will produce a mirror image that is non-superimposable. And so therefore its mirror image is not the same as the original. They're going to be 2 completely different molecules, and they're only related by this idea that they're mirror images of each other. And so let's go ahead and talk about the next 2 carbons, the one that shares a double bond. So whenever you guys have a double bond or a triple bond, their connections are the same. And so therefore, we have something that's achiral. So automatically for double bonds and triple bonds, those carbons are automatically achiral. For this carbon that's on the right, notice that's bonded to 3 hydrogens, and so once again this carbon is achiral. So it looks like overall this molecule has 1 chiral center, or 1 chiral carbon. Oops. But even the presence of one chiral carbon or one chiral center will make the whole entire molecule chiral. So in other words, its reflection is an enantiomer. All right, and so let's go ahead and focus on this molecule. This carbon right here is bonded to 3 hydrogens. And so since those hydrogens are the same thing, then that means that the carbon, that carbon is achiral. Let's go ahead and focus on this carbon right here. This carbon is attached to a hydroxyl group, a CH3, another CH3. So since both of these are the same thing, then that means this carbon that's on the center that I've highlighted in yellow is achiral. And so if you guys are looking at this carbon that's to the right of it, it's bonded to 2 hydrogens. So if you have atoms, if you have the same atoms bonded to that same carbon, then that molecule is, that carbon is achiral. So same idea with this CH3. And so it turns out that all of these carbons here are achiral, making this whole entire molecule achiral. So therefore, its mirror image will be the same. So let's go ahead and take a look at this next example. And so here we have these molecules. So I'm just going to go ahead and quickly highlight these carbons here. Okay. So the carbons that I've highlighted, it's bonded to at least 2 of the same atoms. The identity of those elements are the same. So therefore, all of these carbons are achiral. Okay. And so what I want to do is I want to focus on the carbons that I didn't highlight. And I'll do that in pink. So I want you guys to notice that the carbon on the left-hand side, it's bonded to a CH3, CH3, an H, and all of this. Okay, so that's everything here is bonded to this carbon. And so since the carbon that's in pink on the left is bonded to the same CH3, then that would make this carbon achiral as well. Now let's go ahead and erase some of this stuff. And let's focus on this carbon. So this carbon is bonded to a hydrogen. It's bonded to this whole thing. It's bonded to this whole thing. It's bonded to this whole thing. So does any of the stuff that I've circled that's bonded to that carbon that's being pointed by the arrow, are any of them the same? And so the answer is no. All 4 substituents are different. They're not the same. So therefore, we do have a chiral center. We do have a chiral carbon. And so since there is a presence of a chiral carbon, then this whole entire molecule would be considered chiral. And its mirror image is going to be an enantiomer of what you guys see. In other words, they're going to be completely different structures because the molecules will not be able to overlap around the chiral carbon, around the chiral center. All right, so hopefully you guys are understanding the idea behind chirality. And so what I want to focus on now is the same idea but using skeletal structures. And so with skeletal structures, I feel like it's a little bit more easier, but for some students they might have a difficult time. So I just want to go through some examples that would demonstrate how to tell if a molecule is chiral or achiral, how to tell if inside a molecule there's a chiral carbon or achiral carbon. And so one of the things that you guys have to do is kind of fill in the hydrogens that are invisible. Okay, so remember that for skeletal structures, everything that you don't see is a hydrogen. And so if we're taking a look at this carbon, since there's one bond, remember carbons needs to have 4 bonds. That means that there's 1, 2, 3 invisible hydrogens. Okay. And so all I'm doing is I'm drawing all of my invisible hydrogens. And I'm going to draw enough so that my carbons will have its octet. Okay. So you want 4 bonds on carbons, always and always. And so looking at this carbon in pink, notice that it's surrounded by 3 hydrogens, so there's no way that carbon is chiral. So I'm going to move on to my next carbon. If you guys are looking at the stuff that's attached to it, there's 2 hydrogens, and so if we have 2 of the same thing, there's no way that that carbon can be chiral. And so if I move on to the next carbon, I want you guys to notice that there's 1 hydrogen, 1 methyl group. Here we have an ethyl group, and here we have this other group that's attached to this central carbon, and none of this stuff is the same, right? Everything that I've circled, none of it is the same with respect to each other. And so we do have, in this case, a chiral center. And so this carbon is going to be chiral. Okay. So let's go ahead and take a look at this next carbon. So once again, it has a hydrogen here, methyl here, has this aldehyde containing group, and we have this alkyl group. And so notice that for the second carbon that's in pink, what's surrounding it are 4 completely different items. And so that would make the second carbon that I've highlighted in pink chiral. And so it looks like we have another chiral center. And so we're going to move on to the next carbon, which is this guy. So notice that it's bonded to 2 hydrogens, and so therefore it's going to be achiral. If you guys look at this carbon that's highlighted in pink on the right-hand side, we have an aldehyde. There's a double bond, so the connection is the same. And so therefore it's going to be achiral. Okay? So any double bonds, triple bonds, it's automatically achiral. And so because we have 2 chiral centers, it actually doesn't matter if we have 1 or 2, just as long as we have 1 chiral center or chiral carbon, then this whole entire molecule is going to be chiral. And therefore, its mirror image is going to be an enantiomer of the image that we currently see. So the mirror image is going to be non-superimposable to the image that we see. And once again, therefore, that mirror image is going to be a completely different molecule than the one that we currently see on the screen. Okay. So hopefully you guys are kind of understanding of where I'm going here. So let's go ahead and do this next example. If you guys are looking at the skeletal structure, first thing that you guys want to do is fill in all of your missing hydrogens. Remember, you want to follow the octet rule. You want to have 4 covalent bonds on each carbon. So if you have a double bond, that's 1, 2, 3, 4. Okay. Here I have 1, 2, 3. That means I need one more, so this is 4. Here I have 1, 2, 3, 4. All right, so now that I've drawn all of my missing hydrogens, I just need to focus on each carbon. So if I look at this carbon, notice that I have 3 hydrogens that are connected to the same carbon, so no, that is achiral. If you look at this carbon, 2 hydrogens connected to the same carbon, achiral. Double bonds, achiral. If I look at this carbon that I just highlighted in pink, I have an aldehyde on the left, or I'm sorry, on the right, hydrogen up, methyl down, and I have all of this, that's on the left-hand side. So all 4 of the attachments that's on that pink carbon are different. So therefore, that carbon is going to be chiral. And if you guys are looking at this last carbon, notice that that carbon has a double bond, so therefore it's achiral. And so it turns out that we only have one chiral center, and since we have at least one chiral center, this whole molecule is going to be chiral. Therefore, its mirror image is going to be spatially different than the molecule that we're seeing, and its mirror image is going to be completely different. It's going to be a completely different molecule than the molecule that we're seeing. Their only relationship is that they're mirror images of each other. All right. And so hopefully you guys understand how to identify your chiral carbons using this skeletal structure. And so you guys are simply looking at carbons, filling in all of those missing hydrogens, and you're going to see if those attachments to each of those carbons are the same or different. If you have at least two attachments that are the same, automatically achiral, move on. Okay. If all of your attachments are different, then they are chiral, and if you have at least one carbon that's chiral, the whole molecule is chiral. Therefore, its mirror image is going to be an enantiomer of the molecule that you're currently seeing. And double bonds, triple bonds, those carbons are automatically achiral. So just move on. Okay. Oxygens, hydroxyl groups, they're not carbons, right? And so since they're not carbons, then we can't apply, this idea of enantiomers to them. Okay? We can only do so for carbons. Okay. And so why is chirality super important? Why did I spend over an hour talking about this? And so remember that the mirror image of those molecules are different with respect to each other. And so because they're different molecules, because the mirror images are different, their biological activity is also different. And so this is an example that it's pretty interesting. And so methamphetamine, just the word methamphetamine, brings up that horrible drug, right? That drug that is associated to, substance abuse. It's associated to this idea of meth, and all these like negative connotations, right? And so it turns out that methamphetamine has one chiral center, and it's located, it's indicated on this asterisk. And so the chiral center, depending on the stereochemistry, this drug has essentially like two forms. And so if you guys have the D or S version of methamphetamine, this is that psychoactive drug that we typically refer to meth. However, if you have the R or L enantiomer, then this drug doesn't elicit the same biological effect that the S and D version of methamphetamine does. The L version is actually a nasal decongestant, and so it's not psychoactive. So it's crazy because we have, this same, well, I shouldn't say the same, we have mirror images of, this molecule, but they have totally two different biological effects, making them distinctly two different molecules. And so if you guys were to go into a drugstore and if you guys were to look at the name, here we have, let me just highlight this correctly, Lev methamphetamine. And so notice how the spelling is different. However, the remnants of this word methamphetamine is still there. And so your vapor inhaler contains this over-the-counter non-psychoactive drug, this L-methamphetamine. However, if you were to, sell or ingest some way, somehow, the D version of methamphetamine, then you guys that drug will elicit all of these, biological effects that we attribute to as meth high, right? Okay. And so another example of chirality is found in, another drug, Ritalin. And so here, Ritalin actually has two chiral centers. So Ritalin is typically a drug used for ADHD. And so what I've highlighted has two chiral centers, two chiral carbons. So its mirror image, the S form, is an antidepressant. Okay. Once again, they're mirror images of each other, as you guys can very well see by looking at the structure. However, two different biological effects, making them two different molecules. And so these two are enantiomers of each other. And so same idea here. We have a chiral center. And so here we have R-limonene and we have S-limonene. And so how we interpret this biologically is the R-limonene has this soft, sweet, orangey odor, but the S-limonene has this hard, acrid, lemony odor. Carvone, same idea here, spearmint versus caraway. And so the only difference is through this chiral center. And so caraway is typically what you guys like put on the seeds of your bread, caraway seeds. So this is an image of the spearmint leaves. And so if you guys were to smell them, they would have two very distinct odors. But if you guys were to look at their structures, their molecular structures, it's literally almost the entire same thing except for one of the carbons, and that carbon has a chiral center eliciting different biological responses. Okay. And so it turns out that there's this drug called thalidomide, and it was synthesized in West Germany. And it was marketed specifically as a wonder drug that provided safe and sound sleep. And so the sedative was found to be effective when given to pregnant women to combat morning sickness. And so, unfortunately, thalidomide, so let me zoom in here. Okay. So thalidomide has a chiral center, and it has one chiral carbon, which is what I'm highlighting. And so thalidomide itself does have this positive benefit of curing morning sickness. However, its enantiomer, its mirrored reflection, causes birth defects. And so, back in the day, these pharmaceutical companies, or these people who are creating these drugs, they were not paying attention to the chirality and the relevance and the biological effects of chirality. And so individuals who ingested the enantiomer of thalidomide that causes birth defects had babies that had, contorted. So for example, here, notice that the bottom half is opposite, right? So typically, like, our butts are in the back, here they're kind of in the front. We have shortened appendages and all of this stuff. And literally, guys, like, the only difference is through one carbon. But it creates this crazy, biological effect. And so if you guys get into organic chemistry, if you guys are getting into like organic synthesis and all of that stuff, drug design, this is something that you guys really have to pay attention, the chirality of these molecules. As you guys have seen through these examples, the mirror image, these enantiomers have complete different biological effects with respect to each other. All right, so why is this relevant in carbohydrates, right? That's the main point of this lecture video. Well, it turns out that the sugars, these carbohydrates, have chiral centers, and there's actually many of them. And so all of the chiral centers are going to be highlighted in pink. Okay. And so that lets you know that, psychose is different from fructose, which is different from sorbose, which is different than tagatose. And so if you guys were to look at the structures, they all have 6 carbons, they all have hydroxyl groups. However, the positioning of these hydroxyl groups with respect to each other are completely different, eliciting different biological responses. Okay. And so that's basically the main point that I want to convey. And so the fact that we have many chiral centers on these carbohydrates produces different types of sugars, even though structurally it might look very similar. And so why is this carbon chiral? Well, it's attached to 1, 2, 3, 4 different, it has 4 different attachments. Okay? And so if I were to erase this carbon is chiral because it has 1, 2, 3, 4 different attachments. Okay. And so here, this carbon has this carbon is chiral because it has 1, 2, 3, 4 different attachments. And so all monosaccharides have many chiral centers. And that informs you that there are, it informs you that the mirror image of, for example, psychose is going to produce an enantiomer, a compound that is completely different than itself. And so the same holds true for our aldehydes. And so every single carbon that you guys see here in the body are chiral. Okay. And so feel free to go into your PowerPoint and try to understand why all of these carbons that I'm highlighting are chiral. Remember, the quickest way to identify chiral carbons is to determine if all of the attachments on the carbon are different. And if all of them are different and none of them are the same, then you have a chiral carbon, you have a chiral center, meaning that its mirror image is going to produce an enantiomer. And that enantiomer is going to be a completely different compound, and it's going to have different physical and chemical properties, even though it's a mirror image of the original. Okay. And so, last but not least, I just want to talk about this idea of optical isomerism. So why do enantiomers fall under this class called optical isomerism? And it's basically through this explanation. And so here we have light, and light travels in all different directions. However, if you pass it through a filter or a prism, then you get polarized light. In other words, you only allow light that that's parallel to the plane of the filter to pass through. Everything else is canceled out. And so let's just say that your organic compound is right in the center here. When that polarized light passes through, and if you have an enantiomer, so that enantiomer is going to rotate that molecule by a certain degree. So for example, this molecule here will rotate that polarized light by plus 5.576 degrees. Now the enantiomer of that same compound is going to bend that, and it's going to bend that polarized light by the same number, 5.576. However, it's going to rotate it the other way. And so this is the reason why enantiomers are known as optical isomers. They bend light the same magnitude, but just in opposite directions. Okay, guys. So I know that this is a long video. Hopefully you guys have understood the differences, this idea of chirality and enantiomers, stereoisomerisms, and how to identify them using, the expanded structure like you guys see here for monosaccharides, and how do I identify them through skeletal structures. All right, so I'll see you guys in the next lecture video.